We want to start our work with logarithms here, and logarithms really are just a fancy way to write exponents. Let's look at the correspondence between logarithmic form and exponential form. Here in exponential form, I have this true statement, 2 to the third power is equal to 8. If I write that in logarithmic form, what I get is log base 2 of 8 is equal to 3. So you see this logarithm is an exponent. Specifically, it's the exponent I need on 2 in order to get 8. So 2 to the third is equal to 8. This logarithmic form and this exponential form are equivalent. Here I have logarithmic form, log base 10 of 0.01 is equal to negative 2. I'll write that in exponential form by saying 10 raised to the negative 2 is 0.01. 10 to the negative 2 is 0.01. Now, the question is that a true statement? And the answer is yes, that is a true statement. 10 to the negative second is 1 over 100, which is 0.01. So exponential form looks like this. I know this is a true statement. This is what it corresponds to in logarithmic form. So this and this really say the same thing about the numbers 10, negative 2, and 0.01. Here's another one. 2 to the negative fifth is 1 over 32. That's in exponential form. I'll write it in logarithmic form as the logarithm base 2 of 1 over 32 is equal to negative 5. And that tells me that 2 raised to the negative fifth power is 1 over 32. Next, I have this expression in logarithmic form. Logarithm to the base 9 of 27 is 3 halves. Let's check that out. 9. That's the base, raised to this exponent, 3 halves, is equal to 27. Now, is that a true statement? 9 to the 3 halves equal 27. The second root of 9 is 3 to the third power is 27, so that's a true statement. That's also a true statement. So you just want to have memorized what logarithmic form looks like in its corresponding exponential form like this so that you can go back and forth between them. Of course, you're going to be more familiar and intuitive with exponential form than you are with logarithmic form to start with, but once you get this memorized, everything's going to seem real easy. Here's some more problems. Let's solve for x. I have log base 3 of x is equal to 2. I'm not as familiar with logarithmic form, so I'm going to change this into exponential form. This is equivalent to 3 to the 2 is equal to x. 3 to the second power is equal to x. So it's always this base to this exponent is equal to this number. 3 to the 2 is equal to x means that x is equal to 9. So that's a pretty simple equation to solve once I put it in exponential form. Next one, log base 8 of 2 is equal to x. That means that 8 to the x is equal to 2. So I'll change to exponential form. 8 to the x is equal to 2. So what number do I raise 8 to in order to get 2? I'm going to write this as 2 to the third to the x is equal to 2. 2 to the third to the x is equal to 2. Let's move it over this way. That means that 2 to the 3x is equal to 2. 2 to the 1. That means that x must be equal to, I'm just going to go down here, 3x is equal to 1. So x is equal to 1/3. Sorry that's so messy, but the idea is the same. I have this logarithmic form right here. This base 8 raised to this exponent x must be equal to 2. So I write that 8 to the 8 to the x is equal to 2. So 8 to the x is equal to 2. I want to solve this equation, so I write 8 as 2 to the third. Then I have 2 to the third raised to the x. That's 2 to the 3x is equal to 2. And 2 is the same as 2 to the 1, so since these bases are the same, the exponents must be equal. 3x is equal to 1, so x is equal to 1/3. Here's our next problem. Let's graph y equal log base 2 of x. Well, I know that its inverse is y equal 2 to the x. So y equal 2 to the x is the inverse of this right here. So first I'm going to graph this, y equal 2 to the x. When x is 0, y is 1. When x is 1, y is 2. And when x is 2, y is 4. When x is negative 1, 2 to the negative 1 is 1/2. When x is negative 2, 2 to the negative 2 is negative is 1/4. And so I end up with this for the graph of y equal 2 to the x power. And I know that that is the graph of the inverse of y equal log base 2 of x. So if I just draw in my line y equal x right here and reflect this graph over this line, I'll have the graph of my function y equal log base 2 of x. So when I reflect this curve right here about this line, I'll get this point, I'll get this point, I'll get this point right here, and then it'll go down this way and this way. So when I reflect that, it looks like this. So that should be the graph of y equal log base 2 of x. So graphing a logarithmic function, sometimes the easiest way to go is to graph its inverse first and then reflect the inverse about the line y equal x to get the graph of the logarithmic function. Let's look at a few more problems. We want to simplify here log base 2 of 16. Now remember, logarithms are exponents, and this exponent in particular is the one I need to write on 2 in order to get 16. So 2 to what power is equal to 16? The answer to that is 4. 2 to the 4th is 16. Next problem, I have log base 3 of 3. What exponent do I put on this base 3 to get 3? The answer is 1. Next problem, log base 5 of 1. I have log base 5 of 1. What exponent do I put on 5 to get 1? The answer is 0. 5 to the 0 power is equal to 1. Now my next problem down here, log base 6 of 6. I'll start inside the parentheses. What exponent do I put on 6 to get 6? The answer to that is 1. 6 to the 1 is equal to 6. Now I can simplify this. Log base 3 of 1. What exponent do I put on 3 in order to get 1? And the answer to that is 0. 3 to the 0 power is equal to 1. So you see, logarithms are exponents, and if you know that about them, you can simplify expressions like this by thinking of logarithms in terms of exponents.